Welcome, everybody. We're going to get started in about 1 minute or so. And Jody, just to make sure you too can unmute and transmit, you're good there?
Hello, I'm transmitting.
Okay, excellent. Welcome to Radio Free Physics. All right, well, why don't we go ahead and get rolling. I'm going to stop sharing the pre-roll slideshow here. And Bonnie, if you want to go ahead and start getting your slide share, that'll buy you the appropriate time to do that. Meanwhile, let me welcome everybody back again to the Physics Department Speaker Series for Fall 2020. We're beginning our November series today, and its theme, which is perfect for the talk that we're going to get today on new frontiers in physics. So in a moment, I'm going to hand things over to Professor Jody Cooley to introduce our speaker, Professor Bonnie Fleming. But before we get started, a small reminder to our audience on Zoom. So to ask a question, you have to write the word speak in the chat window. So make sure you have the chat window up and you've got it handy. So in case you have an urgent question, you can let the hosts know. We'll get you unmuted. We'll interrupt the speaker at the next appropriate boundary if it's during the talk, like at the end of a slide. And then we'll get you pulled in so you can ask your question. Otherwise, you can use that at the end to put yourself kind of in a Q&A speaker queue for the open Q&A at the end of the presentation. And to control the whole, stomping over everybody's microphone on Zoom, because Zoom doesn't handle multiple people talking simultaneously. We do this so we can kind of control the flow a little bit here. And for all the folks on the YouTube live stream, and there are a few people watching on that today, welcome. And this event is being recorded and simultaneously live streamed to YouTube. So that's all the basic boilerplate announcements. Let me now welcome Professor Jody Cooley to introduce today's speaker. So Jody.
Thank you, Steve. So I'm really pleased to introduce today's speaker, Bonnie Fleming, who is a professor of physics and the director of graduate studies at Yale University. In her research, she studies neutrinos to both understand their nature and learn what they can tell us about the rest of the standard model of particle physics and the universe. In her research program at Yale, Professor Fleming is pursuing next-generation precision neutrino detection techniques, combining a rigorous R&D program on liquid noble gas detectors with pressing questions in neutrino physics. Professor Fleming is the founding scientific spokesperson and now the co-spokesperson of the microboon experiment, and also collaborates on the short baseline neutrino experiments, ArgoNeut, LARIAT, SBND, and the Dune long baseline experiments. Her work in the community has included membership on a number of advisory panels, including the DOE's Nuclear Science Advisory Committee, the ICFA Implementation, Innovation, and Development Panel, and she recently co-chaired the DOE's OHEP BRN study on high energy particle physics detectors R&D, which is the topic of her talk today. Combined with her research program and community participation, Professor Fleming actively encourages women and girls to pursue science through mentoring in several programs, including the APS Conference for Undergraduate Women in Physics and Girls Science Investigations. Professor Fleming was elected a Fellow of the American Physical Society in 2014 and received the APS DPF Mentoring Award in 2018. Bonnie, it's a pleasure to have you here today. Thank you very much for agreeing to speak with us.
Thank you, Jody. Can everyone see my slides?
Check. Yes, they're being shared and we can hear you fine.
Great. I'll go ahead and start. It's a pleasure to be here, even if virtually. I have to say, I have family in Dallas and I've long wanted to come visit in person. So I'm a little sad that my first talk at SMU is virtual, but I suppose it is the way it is. And I'll look forward to we all look forward to the future. I'll just leave that at that. So it's a pleasure to talk about the this BRN report today. A little bit different than usual talks I give talking about my work. This is instead this panel that I co-chaired along with Ian Chipsey, and worked with many excellent conveners, including Professor Cooley. So that's what I'll be talking about today, the outcome of this year-long study on instrumentation. And these studies, basic research needs studies, the shorthand is BRN, have been done in across DOE in a number of different areas, including in dark matter within OHEP, but also in basic energy sciences. And they're a way for the agencies to take stock in one area and gather community input and experts input and decide the next direction to go. And so it was a big undertaking. It took a year, as I mentioned, and I'll talk a little bit more about the process and the outcomes that we came to. Oops, okay. So the talk that I'll show today has significant overlap with the presentation that Ian and I gave on behalf of the whole panel to HEPAP, the High Energy Physics Advisory Panel, the community panel in high energy physics. I hope nonetheless to minimize jargon throughout the talk so you get a sense of the whole process and what we learned and the direction I hope we'll be going. So as I said before, this was a huge effort by a lot of people, and I circled Professor Cooley in this picture in one of the culminating events of this year-long study, which was a 4-day workshop in Rockville, Maryland at the beginning of December of last year. Maybe that was one of the last times we've traveled, really. And here we are in a picture of all of the panel members. And I'll talk a little bit more about what roles the different panel members served. But let me start, before I get into some of those details about why we embarked on this process at all. And it goes back to really why we, in particle physics, embark on the science that we do. And it's the opportunity for discovery of some of the most interesting, pressing, and fundamental questions in the universe that comprise our makeup, the mystery of the Higgs boson, the mystery of neutrinos, which are all around us, the mystery of dark matter and dark energy, which comprise an enormous amount of the universe, and yet we still call them dark, which basically means we don't know what they are. Understanding how different particles interact and make up the matter, and the confusion of the matter, antimatter, asymmetry in the universe, all the way down to the mystery of gravity. So this is a really, these are questions that scientists have asked for a long time. Right now, I would say we are very much in a data-driven era when we have lots of interesting results from experiments and plans for experiments in the future. And the thing that we need to enable those future experiments is new technology. If history is our guide, new technologies bring new discoveries. And so that's an underpinning for this whole report. What are the scientific questions we want to answer? And how do we develop new ideas for new tools to be able to get there? This is encapsulated well in this lovely quote, which I'm going to take the time to read, which is that new directions in science are launched by new tools, much more often than by new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have yet to be explained. Measure what is measurable and make measurable what is not. I really love instrumentation. I love the science questions more. We are here to try to answer those science questions, but if we can do so with new innovations in instrumentation, it'll accomplish the science and then more. And it's also really fun, I have to say. Okay, so this whole report, which took a year to research and write, it led to a number of what we called priority research directions that spanned the different technologies that we reviewed. And I'll talk about them later in the talk. We boiled down all of the instrumentation that came out of this report, however, into 4 grand challenges. And these are the 4 grand challenges which we use both to be able to summarize the report in one way, and also as an inspiration, the kind of thing that inspires Congress to put more money, for example, into instrumentation, just to say a little bit bluntly, but it's really more inspiring than that. And I'll read them off, but I won't read the fine text. I can let you read that later. Advancing HEP detectors to new regimes of regimes of sensitivity. Using integration to enable scalability for HEP sensors. Building next generation HEP detectors with novel materials and advanced techniques, and mastering extreme environments and data rates in HEP experiments. So all of what we thought through as future technologies fit into these 4 broad categories. Let me say a few words about the process of the report. As I said before, we were charged by the Department of Energy to write this report, to form a panel to be able to develop and then write the report with the goals of surveying where we are now. What's the current landscape of HEP technology? What drives the science? Where do we need to get in terms of capabilities and performance for detectors to be able to accomplish the science that the field wants to do? Identify technologies to provide or enhance those capabilities. Where do we want to go next? Do we need an order of magnitude better for a certain sensor, and what will that get us in terms of the science? To articulate all of these things into priority research directions, which we call these PRDs, to push beyond the current state, to flesh out research programs that guide the R&D efforts in each area, and to formulate these 4 grand challenges. That was a little bit boring, but let me go into the details. So what's the science that's driving the field? The science that's driving the field, we fell back on the 2014 P5 report that highlighted 5 science drivers that span particle physics. And and this includes Higgs as a new tool for discovery, the physics of neutrino mass, the physics of dark matter, cosmic acceleration, meaning inflation and dark energy, and exploring the unknown. We then looked across technologies, and we classified the technologies into 7 technology panels listed here: quantum sensors, solid state, calorimetry, readout and Asics, photodetectors, noble liquids, and TDAC. And for all of these physics panels and technology panels, we recruited excellent people like Professor Cooley to chair and build a group of people to be able to flesh out, in terms of the physics, what's being done now and what are the future prospects. In terms of the technology, the same thing. We also had a cross-cutting panel which looked across all of the physics and even more so across all of the technology, because there are areas which you can probably see where there's either redundancy between these different technologies, or even more worrisome if there's something that we might forget that has to be somewhere. So we tried to find a way to make sure that we were thinking across all the different panels in a comprehensive way.
And if I can interrupt you for a second, Bonnie, we have a question from Tom Cohen. So Tom, you should be able to go ahead and unmute now. All right, so just in case.
Sorry. So, yeah,
sorry. Perfect.
Sorry, Bonnie. I think you just answered my question. I just wanted to know who, besides you and Chipsy, who the panel of worthies was. But I see on slide 1011 you enumerated these guys.
Yeah, you can see all the conveners. I'm pointing. It's not. You can see all the conveners here listed, and in a later slide, I have a more detailed listing of all of the people. Each working group consisted both of the conveners and another group of people that worked with them that they recruited. Good. Okay, so we started in summer of 2019, and we had many regular telecons leading up to the December workshop that I talked about and showed you a picture of in early December in Washington, D.C. And based on all of that and all of the work at the workshop, we laid out a report, which we then spent several months into 2020 finalizing and eventually presented in July to HEPAP. And I think I just got an email from DOE today that it's officially on the DOE website. So today, what a day for that to happen. What we thought of as study hallmarks, real close interaction between the physics and the technology group, and to have this cross-cutting group that looked across for synergies between different groups and made sure that everything made it into a group. We also worked really hard to get input from the community, and we did this through CPAD, through community surveys, through town hall meetings, through small targeted workshops, some which we did broadly across the BRN, and some which each individual group did on their own. Here you can see, this was your question, Tom, the full list. I won't spend a lot of time on it, but it's here. You can see the full list of the physics panels and the technology panels, 2 co-chairs, 24 panel leads, 35 panel members, and 5 in the cross-cutting group. We worked hard to balance this group that developed all this work across a bunch of different metrics. Here are a few. There were about 60% of the panel members from university and 40% from national labs. There was a pretty equal gender balance as well. Here's an example of one of the many ways that we took a lot of input. We worked with CPAD, in particular in coordinating with their instrumentation frontier workshops, both with the report they wrote from the 2018 workshop and by many of the panel members giving talks at the 2019 workshop and interacting actually in person with lots of people at CPAD to gather in community feedback and fold into our own meeting in December, which happened just after the CPAD workshop in December, early December 2019. And here finally we get to maybe the last of my process slides, which is our very intense 4 days in the basement of a hotel in Rockville, which is how those things go. But it was really wonderful, actually. It's really nice to have everybody together to be able to see how one group is doing something, learn from that and cast that onto another group, talk about synergies between groups. For example, as an example, photodetectors and noble liquids, there's lots of synergies between those 2 technologies in certain areas, that kind of thing. Okay, so let me say a few words about the structure of the report. It was very difficult to sort out how, in particular with a topic like instrumentation, you could bring it all together. There's lots of different kinds of instrumentation. They can have impact on many different areas in HEP. How could we bring it together in a cohesive way? And so we started with the science. These defined technical requirements, and then we had a set of priority research directions which responded to the technical requirements. These priority research directions were associated with these 7 technology panels, while the technical requirements were defined by the physics panels. So what physics do we want to do? What are the technical requirements to accomplish that physics, and what new technologies do we need to meet those technical requirements? And we thought about it in these ways. And then for all of the PRDs, how do we summarize them into a set of these 4 grand challenges? And the crosscut panel, as I mentioned, encompassed all of these and looked for synergies between the science drivers and the technology panels, but also within the physics panels and within the technology panels. And we ended up here again at the 4 grand challenges. We did all of this in what we thought of as a development ecosystem. it's not only important to consider what the new technologies are, what's required by the physics and what we can think about in the future, but how are we going to do it? So we thought a lot about that. So key to the success of future instrumentation development, or so-called tool revolution, are the people and the facilities and the resources to accomplish that, and the connections and the collaborations that they make. So we started by thinking through this in terms of the workforce, the facilities, and these connections. In terms of a workforce, we thought carefully about a commitment to equality, diversity, and inclusion in HEP instrumentation R&D. Excellence and innovation come most effectively from diverse teams of people. And it's critical to start with this. And I'm going to read it because I think it's important to read. To accomplish the best science, we must commit as a community to action to overcome the social injustices in our own backyard and realize the impact of a diverse workforce. We must find, develop, and invent new ways to attract, encourage, recruit, and support a diverse community. We must enact an inclusive environment within instrumentation and within particle physics at all levels and across the areas in which we work and that we touch, including in academia, in universities, in national laboratories, and in industry. So we noted that there are some small steps that are already being taken to draw young people from diverse backgrounds into instrumentation. And that includes outreach programs at universities and national labs and to the public, the undergraduate research opportunities through the agencies like the NSF REU experience, and through CPAD, the Graduate Instrumentation Research Awards, which have been really successful and have been awarded to a pretty diverse group of people. In addition to those JIRA awards, which I recommend you nominate your students for, there's also the DPF Instrumentation Awards, and on the bottom you see the most recent recipients of those awards. But note that while this is a start, the scale of these initiatives must be dramatically increased and new initiatives developed with urgency. We also talked about workforce requirements. How do we train and keep and train a workforce in instrumentation in our field? To succeed in creating tools and technologies, we need to train the next generation of people, and that includes a pipeline. That includes university lab partnerships, connections to other disciplines, and appropriate recognition. I think this is a problem in our field. There used to be more support through the agencies for folks who really focused on instrumentation at universities. And I would say in the last 15 years, that's decreased a lot as the budgets have been tightened. That's my experience. And that's a problem because many of those scientists and engineers, detector junkies, I sometimes call them, really took new ideas wherever they were and ran with them for new ideas in instrumentation. So I think we have to think carefully about and push within the agencies for support for that kind of scientist and engineer that really excels in instrumentation, and give them the recognition that they need to be able to succeed and to be able to train the next generation of people like that. Okay, unique capabilities and resources. We have a bunch of unique capabilities in the field. Many of them, maybe most of them, at national laboratories. SciDet, the Noble Liquid Test Facility, Microsystems Lab, the test beam at Fermilab, test beams at SLAC. And so we tried to think carefully about what new capabilities were needed in the field, folding in where we could collaborate in order, even internationally, in order to accomplish the facilities that we need. And here you can see a table where you look across science drivers and then down with facilities. What do we have and what do we actually need? Connections to other programs, other offices, other agencies. I won't talk about, but we always need to try to connect with other agencies. There's overlap, for example, in technology in this report for neutrinoless double beta decay. There's an overlap between OHEP, where there are scientists who work on it while it's primarily funded by nuclear physics. So you'll see that that instrumentation is written about in this OHEP report, but it's really funded through nuclear physics. Those are stovepipes I don't particularly like to pay attention to, but they exist, and anything we can do to make connections to other programs, we should. Connections to other disciplines is also critical. I think we don't enough call out the benefits to society for the things that we do. And there are lots of good examples, and I'll just show you the pictures here. You know many of them. And so what we hoped, and I'll highlight what's in yellow at the bottom, the instrumentation plan described in the report, we hope would lead to the development of new technologies that hold the promise to be as broadly applicable and transformative as some of the things outlined here. Okay, going back to the 4 grand challenges, and now I'd like to get into some of the details of the physics and the technology panels. And I'll start with the physics panels. I mentioned before, the physics panels are aligned with the 2014 P5 science drivers. And the first is the Higgs and the energy frontier. How I think we went, we looked more long-term, and I think than the P5 panel did. We followed the science drivers. We looked back at that report. We thought, where is the field now? And where might the field go? We were cognizant as an instrumentation panel to not pretend to do the job of a P5, but nonetheless to look forward to what are all the options on the horizon? And for any of those options, what do we need to do now for instrumentation to be prepared for that? And so that's what we did. And each of the science panels defined high-level goals. Here you can see Higgs properties with sub% precision, Higgs self-coupling with 5% precision, Higgs connection to dark matter, new particles and phenomena at multi-TeV scale. And as I mentioned before, this table is far too small to read, but the point of the table is to take these high-level science questions, describe the measurement needed to accomplish them, and then write down the technical requirement to get there. And those technical requirements in turn drive the technology panels to define priority research directions to address them. Okay, we cast all of these science goals onto long-term timelines. And just to note, the timeline goes from 2020 to 2045. That's a long time. And across the top, you can see experiments, again, broadly defined. This panel is not SNOMAS nor a P5, but we've all heard, 100 TeV proton-proton colliders talked about. So we cast it on there with a fuzzy arrow. And the main point of this panel is to look into those different technology areas: TDAC, solid state, readout, photodetectors, calorimetry. I don't know if you can see my mouse or not. And the different challenges defined by these priority research directions that we need to accomplish by a certain year to be in time for these physics goals. So again, the study is an instrumentation study, but very physics driven, starting with the physics and working our way down to what technologies we need. We did this in all 5 of the science drivers. This is neutrinos, push the 3 flavor paradigm, explore unknown territory, new physics, hunt for new particles in the neutrino sector and other sectors using neutrino detectors. And here you can see a graphic that shows in neutrino physics the challenge of looking from the MeV scale to the PeV scale in terms of different neutrino experiments, which actually makes instrumentation defined in neutrino physics very broad because it spans many different scales and types of detector technologies. Here again, you see the same kind of timeline, although very different than the collider timeline, because neutrino physics has many different experiments that span different questions in neutrino physics that occur again, over a broad range of time, and the different PRDs that factor into that. In dark matter physics, here again, I highlight Professor Cooley's role as one of the conveners of the dark matter group. Search for WIMP dark matter towards the neutrino floor, search for particle dark matter with low masses, search for wave-like dark matter, search for the annihilation or decay products of dark matter interactions. And again, the science drives the measurements, which drives the technical requirements. Here you can see the timeline for dark matter, where less so specific experiments and more so categories of experiments like generation 3 dark matter experiments, enhanced indirect detection, etc., axion searches, generally speaking, which drive, again, over a 20-year horizon, the different technologies we need in the different areas. Cosmic acceleration, drive cosmological measurements to new scales, explore inflation, dark energy, and dark matter, study neutrino physics in a context complementing terrestrial techniques. You can see in some areas, even in the physics, there's topics that span different physics areas. And again, the cosmic acceleration timeline, where here you see some specific experiments and then next generation experiments. And finally, explore the unknown, which is a little bit of a grab bag. That was true in the P5 era too, but precision measurement in heavy flavor decays, searching for charged lepton flavor violation, tests of CP violation through EDM searches, probing the dark sector, and hunts for new physics, new fundamental forces. And in Explore the Unknown, we had 3 different timelines that were across 3 different classes of experiments: EDM experiments, flavor physics experiments, and then rare muon decay experiments. Okay, so now let me move on to the technology panels. The technology panels defined the PRDs. They went beyond this. I've talked a lot about the PRD's connection to physics. How do we make that connection? But once you've defined these PRDs, the technology panels went on to really flesh them out in more detail. What thrusts and actionable research plans might come from pursuing that particular PRD. And the goal there was in part for the agencies, for them to be able to see a little bit beyond the concept and see that it was realizable, even if realizable is a 20-year timescale. So in calorimetry, you can see, I'll go through all 7 technologies like this, and the top is just the name of the PRD and the technical requirements which ties them to the physics goal. And the bottom talks about connections outside of HEP and realizing the facilities and capabilities needed for each. So calorimetry is broadly defined by these 3 PRDs, which encompass energy resolution, spatial and time resolution, radiation hardness R&D, and finally developing ultra-fast media for background rejection and particle ID. The next panel are noble elements. Noble elements has more PRDs. They include, broadly speaking, enhancing and enabling modalities in detection and developing new modalities, new ways for detection. Better understanding and characterizing the microphysics of noble liquids to help us understand what's actually happening inside detectors. Advanced purification of noble liquids and assay methods of anything you put in a noble liquid. And finally, addressing the challenges needed to scale these detectors to the very large sizes. On the lower right, you can see a very small noble liquid detector, but the Dune experiment plans to have 70 kilotons of liquid argon. So we're scaling from very small to very big sizes. Okay, photodetectors. The photodetector PRDs focus on detection across extended wavelengths, broad list of wavelengths and down to single photon precision, advanced spectroscopy, precision timing, development of optical coupling, and as in many of the other technology areas, adapting to extreme environments, which is a big challenge. High radiation, most notably. Connections outside of HEP, which I haven't highlighted in some of the previous ones, but they're on my slides, but here include astronomy, medical imaging, biology, and here as well, some of the, not workforce, but realities of the field are, close connections to industry, and many of these areas are important for fabrication and procurement reasons. Okay, quantum sensors. Quantum sensors come in many forms, ranging from qubit technologies to NMR-based sensors, and in some cases, gravitational waves. The PRDs you see here span increasing sensitivity to surpass the quantum limit, increase the sensitivity by enabling ensembles and networks of sensors to work together, enhancing low threshold quantum calorimeters, and enabling new technologies. Readout and Asics. Again, here we have two PRDs that, broadly speaking, encapsulate developing Asics in particular to handle extreme environments of high radiation, high data rates, and low temperatures. So a lot of issues with respect to extreme environments, and also the need to create systems, blocks of systems on a chip for these environments. So many all in one chip. Again, here, there's an issue with respect to industry. Foundry access is critical in this area. And there are very few foundries that will engage in this work. So not only workforce development for people who develop these, which tend to be specialized scientists and engineers, but also connecting them to the right people who can fabricate them. Solid state and tracking. These three PRDs are, broadly speaking, focused to significantly improve resolution in space and time in high density environments, and to explore alternative to silicon as the active medium, which can improve, for example, detection in cosmological studies. And finally, almost finally, TDAC. And TDAC was really driven by high rate environment issues. How can our data-driven era, which is characterized in OHEP by large volumes of data, and often, again, in extreme environments, how can we scale up even beyond that for the next generation of experiments, for example, future high-energy PP colliders, and to develop systems that both can scale up and even get better with respect to timing resolution. Okay, so that was intense whirlwind for me, even speaking. Those are our 7 technologies, and just some of the things that we thought about in pulling all those technologies together. And we tied this all together, hard to see here, but into the 4 grand challenges. You can see the color coding that associates the different PRDs with each of the grand challenges, in blue, in brown, in green, and then in yellow. And you can get a sense of the grand challenges are quite broad. However, they tie to many PRDs, but you can see a connection there. Good. I'm a little faster than I thought I would be, but maybe that means that there'll be time for questions. So why did we write this report? What to do with this report, and why now? And there's a couple of reasons for this. So first of all, it's timed because I would say, my personal thought, instrumentation is the underpinning for all of the experiments that we do. which are driven by the science. We're approaching a year-long community planning exercise, SNOMAS 2021, and it was a good time to survey where we are and where we think we're going with respect to instrumentation leading into that. So we start with this report by essentially handing it over to the physics community and hoping that what's laid out here can be built on and developed in the process of SNOMAS. What's achievable if we can accomplish these instrumentation goals. Finally, we work in a global context, and the European strategy report, the 2020 update was out at the time of this past summer. And that report states the community should define a global detector R&D roadmap that should be used to support proposals at the European and national levels. So we thought both relevant to think about instrumentation leading up to SNOMAS, but also in the broader context of the global community. And frankly, to learn from the global community, which do a good job with large R&D collaborations, much more so than we do in the US. And that's it. I'll finish there. I'm earlier than I thought I would be, but again, I welcome any questions. And I want to make sure to say that while Ian and I chaired this report, there were enormous contributions from all of the conveners, the panel conveners like Professor Cooley, and all of the panel members that worked with them and with us. And then we worked hard to get input from as broad a slice of the community as we could. And we also got final feedback from experts in the field, final readers of the report before we submitted the final report. And as always, we benefited from professional assistance from DOE. I'll end on a much better slide than that. Thank you.
Okay, no, thank you very much, Bonnie. And people are free to hit the Zoom applause button, but that all kind of falls flat. So we're going to try something else. We like to give just a little bit of canned applause here at the end. It's better than the alternative.
It's great. You guys it's very professional, I have to say.
It's the flat soda of fun beverages on a Monday afternoon. But all right, this is great. Thanks for wrapping up. This leaves plenty of time, actually, I think, for questions and discussion. This is fantastic. I see we have already a request to speak from Tom. So Tom, I'm going to ask you to unmute and you can go ahead.
It's a very nice talk, Bonnie. One issue which is somewhat aligned with what you talk about is at many universities, if you have an idea for instrumentation, often to flesh it out in order to make a competitive proposal or even to write a better preprint that you'll dump on the archives, you need access to specialized engineering. At provincial schools like my own, we are never going to get funding to support a local engineer. However, if there were such a program, say at the national labs, whereby those engineers could allocate 10% of their time to serve university community as a whole and have some mechanism to vet proposals, I think that would leverage the many of the unused brains that are sitting out here in the provinces.
Yeah, thank you for bringing that up. We talked about that. First of all, I couldn't agree more. You know, and people have tried for a long time to push the agencies to somehow have a system where you can connect with the national lab teams of different kinds of engineers. And the current system is if you know the right person, then you can find a way to work with them and accomplish a fair amount. But that's not the right system at all. And the money in the field for supporting individual engineers, even at big universities, has gone down dramatically in the last decade, as I mentioned. So we talked about this a lot in the context of workforce development. That's why I spent a fair amount of time talking about not just how do university scientists have access to those people, but how do we make sure we actually have those people in 20 years? It's sort of a specific brand of person, and we don't even treat them very well, in my opinion. So I agree. I don't know the solution. We brought it up a lot with in discussions within the panel, but also with the crosscutters and with Helmut. And I think the agency would like to, I don't want to speak for him or the agency, but just to say that I think that they would like to find a solution that's better than the current system. I don't think I really answered your question, but I did my best to say I agree with you. It's a problem.
Yeah, Tom, did you want to make a follow-up comment or question based on that? All right, if you do at any time, just type speak again in the chat window. Once you mute, we can't hear you. It's the folio. Oh, there we go. Perfect. Excellent. All right, go ahead, Tom.
No, it's just heartening to hear that people at least are discussing this. I think it's just a problem for the field as a whole, and it doesn't seem like it's an easy problem to solve. But there's a lot of unfortunate inefficiency hardwired into the current way we seem to get technical access to those of us out here in nowhere's land.
Boy, if Dallas is nowhere's land, we're really screwed.
There's some successes. Let me say one success, which has to do with instrumentation, which is that Fermilab's PrEP, I don't even know what PrEP stands for, but at least different from 10 or 15 years ago, will loan out equipment in a very easy way. Like they have a website, and these are things like, small power supplies, NIM bins, the kind of thing you would need to do a small setup in a lab that is otherwise hard to find and would seem silly to buy. And you can go to PrEP's website and click on what you would like to borrow and write up within the website a collaborative agreement to be able to borrow it. I don't think it's well advertised, but it exists. And Fermilab works with Argonne in upgrading this equipment to be able to loan to people. So there is some recognition that's a instrumentation, not a people issue, but to try to make some resources that are in the community more broadly applicable and available.
No, I've used PrEP in the past. My issue is always getting access to the technical brain.
Yeah.
Okay, Richard, you had a question. Go ahead. You should be able to unmute.
Hi, Bonnie. This was very nice talk. I enjoy that. I want to follow on Tom Cohen's question to some extent, that the essentially reduction of the technical infrastructure at the universities has been much longer than 10 years. I mean, when I came to the States 45 years ago, the 60% of the high energy physics budget went to universities, and now it's only 20% or something like that. And that allowed people to do research locally. So what do you expect will be the outcome of this report, in a sense that it's easy to, I mean, it has been a big work, a very nice result, and what prevents it of being put on a shelf?
That's a good question. I can tell you what we hoped from the beginning would be that outcome, and let me start there. There were a couple of different outcomes that we were going for. One was to try to bring all of these different technologies, to write them down in a cohesive way, so that and in a cohesive way, but generated by the community, so that when the agencies are doling out money for instrumentation, they're doing so with some kind of guide that came from the community. better than, frankly, Helmut just deciding who gets what money. Of course, there are comparative reviews on the instrumentation frontier, but that was one goal. The second goal was to write an inspirational report to bring new money into the field. And it's one of the reasons why we wrote things up in terms of grand challenges. What are the things that could be absolutely transformational, and write them down in a way where DOE can go to Congress and get new money. And there are ways that that happens, like the Quantum Initiative Act. That's a whole lot of new money that comes into the field. So how can we think through what are the most inspirational ways to be able to bring a case to Congress for new money? And that second goal, so we can talk about either goal, but that second goal involved, for example, putting together a brochure and going to Washington. And some of those things have slowed down for obvious reasons. Nobody's going anywhere. So I hope that we'll pick that back up again, but it's been a trying time to be able to roll out a report like that. That's what we hope to do, to roll it out. But to first order, those are the main goals, and the hope would be that it will get more money in the field overall.
Thanks. Is there any hopes that one can get NSF involved in that as well? Because it's good to have more than one prong of attack on the politicians.
Absolutely. I would think the answer would be yes. I can tell you how NSF was involved in this report. This was funded and generated by the DOE, but we invited NSF along the way to participate. For example, NSF did call in for the plenary sessions at the December meeting. And so we tried to include them along the way, and as much as possible. In terms of how they fund instrumentation, it's different, frankly, than how DOE funds instrumentation. But in terms of getting more money in the field, I think everyone would be happy with that. So in that sense, yes, I agree.
Thank you.
All right, and again, if anyone else has any more questions or comments they'd like to make, please go ahead and type the word speak in the chat window. While we're waiting for other people to do that, Bonnie, do you mind if I ask you a question?
Please.
Yeah, so the phrase quantum computing is peppered throughout the report, right? So if you flip through the report, it's obvious there are many places that touch on the concept of quantum computing. And I bring this up because you brought up the Quantum Initiative Act a moment ago, which was perfect for the question I wanted to ask. So there's some obvious things like photonic sensors or photosensors that might have an impact on the development of quantum computers. But I wonder, was anyone who's specifically involved in the engineering of quantum computing systems involved in the BRN report? And do you know how this report would read to a group of engineers who are currently like just trying to add 1 or 2 more qubits to a computing system? They're not really thinking necessarily per se about the applications of this beyond, say, cryptography. Are there places they can look in the report that would say, ah, great, these are places where we could apply for new money and it would have this kind of physics application in this field?
I don't know how well I'm going to answer your question, just because this is not my area at all. I could start with photodetectors as quantum sensors, and then I get a little lost. So I don't think I'll be able to answer your question. These were the leads, Andrew Garassi and Kent Irwin, who do have a lot of experience in quantum sensors. And this was I think and you can read the PRDs here: advanced quantum devices, enable quantum ensembles. I think that's what you were asking about. And sensor networks, advanced state-of-the-art and low threshold quantum calorimeters, and advanced technologies in quantum sensing. How much did we go into compared to some sort of advances in industry? I can't answer that.
Mm-hmm. Yeah, no, I mean, I guess if I were an engineer at a university like SMU and I was doing some fundamental research in quantum computing in my lab, and I was wondering if there are ways to partner up with physicists now, not only to solve my problem, but to solve their problems too. Yeah. I wonder how an engineer reads the report. Like, what's the most useful way for them to do that, I guess is where I'm going with this. Because there's not one section on quantum computing per se, right?
There is.
Oh, there is. Okay.
Yes. Quantum sensors was one of our 7 technology areas.
Okay. All right. So I guess I just mistook quantum sensors and quantum computing are deeply connected to each other. And I think that was a mistake on my part in not reading it that way. So
I don't think I answered your question very well, but that belies my lack of knowledge about quantum, which I thought I knew quantum mechanics when I took it as an undergrad. But anyway.
Well,
I thought everything was quantum. Didn't we know that already?
And I remember understanding it. So
that's the best I can answer.
Yeah. All right. Any more comments or questions? This has been great, Bonnie. All right. I don't see anything else popping up in the chat window. So I think at this point we can thank you for this fantastic presentation. Thank you, especially as the co-chair of the committee and the other members of the committee for the long effort that presumably went into this on a very short time scale.
And thank you, Jody.
Yes, I may or may not have heard something about that through the grapevine. Okay. And Tom asked, can we Uber food to Bonnie? And the answer is yes. Hypothetically, the answer is yes, we can Uber you food. We have learned we cannot do a tax-free account with them, though. We have been investigating that in case anybody cares about that in earshot. So it's a work in progress, Tom.
I just hope sometime soon I'll be able to visit you in person.
Yeah, well, and I should let everybody know that I shamelessly, in my letter of invitation to Bonnie, mentioned that hopefully when we return to being able to be in person again, we can plan for some very nice symposium where Bonnie perhaps could come and speak. So that was the carrot that I dangled out there to sweeten the deal on a virtual talk. All right. Well, thank you very much, Bonnie. And thanks to everybody for participating today. And we'll go ahead and wrap it up here. So stay safe, everybody, and have a good evening. Okay.
Thank you.
All right. Bye-bye.
Bye.
Bye, Bonnie. Thank you so much.
Thank you, Jody.
It's good to see you again.
Nice to meet you. Bye.